Let's say this is the car. Two wheels. And an EEC rider. We'll make the EEC green. Because it's a green machine, isn't it? Is pushing. So like you saw in my other video, we had a diagram of an EEC rider. Well, in this one, he's pushing a car, isn't he? See that? Makes sense. That's what we're looking at. And that's it. That's the equation. It's a monster. But that is the equation that will give you the answer to how fast this car is going to go. How fast? That fast. And you might think, what the hell does that mean? Well, you got to plug in the numbers. It depends on so many variables, doesn't it? How heavy is the car? Well, we're going to say 1,400 kilos in our example. How dense is the air? Coefficient of drag? That depends on the car's design. The area, surface area, again, depends on the design and how big the car is. Coefficient of rolling resistance depends on your tires, depends on the road. Your mass, again, depends on the car. Gravity, pretty much constant. That's everything. So if you look at all the terms in this big ugly equation, they're all found on this list here. So now we can just go ahead and work it out. The answer is 1.7712 meters per second. I don't know if you can see the screen on the calculator here, but we've got that equation, that bit in red, we've got it on here on the calculator. This is a pretty cool calculator. It like shows you the exact equation you're putting in. Maybe you can't see that, but anyway. The answer is 1.7712 meters per second. V equals 1.7712 meters per second. In kilometers per hour, 6.376. 6.376 kilometers per hour. And in miles per hour, 3.96 miles per hour. But what we wanted to find out was how far could we push this car before the battery runs out. To find that answer is very simple. All we've got to figure out is how long can we push it for. 6250 seconds. So it's that many seconds. We're moving at that many meters per second, right? 11,070. That many meters, which is 11.07 kilometers, which is equal to 6.88 miles. So there's your answer. That's the final answer. And that's what we came to see.
It's a good first test, isn't it? Right, let's get it going. We seem to be rolling, which is good. You all right in there, mate? Yeah. Good man. Gone really far? How far is it to your house? Whoa. Using no fuel at all. How good's that? No fuel. No fuel, mate. Not using any fuel. Where do you want to go? Straight on down that way? Or this way? Go round to the right here? Well, I thought, you know, to make it more efficient, you cut through the middle. It's what? It's really hurting my arms, this.
Alright, so I thought I'd just show you that it's possible for a 16X to push a car, which is exactly what Ian was doing there from Speedy Feet. But you might be thinking that my equations are wrong, or my calculations are wrong, where said it could go 11 kilometers. So based on my calculations, the King Song 16X can push that car for 11 kilometers. Sounds like a lot, doesn't it? For this little toy to push a car for that long. I mean, some of the original EVs only had a range of like 30 kilometers. That's pretty crazy. And so you might be thinking that, nah, Ark, the only crazy one is you. Maybe you just got up here and posted a bunch of gobbledygook. There's no way the 16X is going to push a car for 11 kilometers. That's longer than most people's commute. And I would understand that doubt people might have, because that sounds like a lot, doesn't it? For a little toy to push your car for that far sounds pretty crazy. So let's look at something that's simple to understand, and that's EV specs for cars like the Tesla, electric cars that run on batteries. They run on these same batteries that we use. The Tesla Model 3 is rated at 0.25 kilowatt hours per mile. That means that you get 4 miles for every kilowatt hour, right? Every mile only uses a quarter of a kilowatt hour, or 250 watt hours. And just to put it into perspective, let's look at because I got the Sherman Max and I've got the Sherman OG. The Sherman Max only has 400 extra watt hours, right? Only. And that's why I say that in quotes, because it's quite a lot. People say, oh, it's only a slight upgrade. 400 watt hours is still a lot. It's enough to push a Tesla for nearly 2 miles. A full-size car that weighs tons. Like, those cars are heavy. So think about that. In the Sherman Max, you've got enough extra, just the extra battery you get is enough to move a Tesla for 2 miles. Pretty crazy. But let's look at the 16X again. So what does that have? It's got 1600 watt hours. If you do the math on that, it can push a Tesla for 6.4 miles or 10.24 kilometers. So over 10 kilometers. There you go. And what did my math say? It said 11 kilometers, didn't it? So it's very close. And that's it. It's verified. But now what we're going to do, guys, and now let's roll that footage, is play the whole thing. Because what you saw there was just the intro and it was all sped up. The whole thing is going to be step by step doing all the math on this one. From scratch, from a blank sheet. We're going to start with a diagram and look at how we approach this problem. And don't go away if you're like not into math, because I do this in a way that it's understandable and it's going to be interesting. You're going to miss out on a lot if you just watch until now and then quit. So let's do it. Welcome back to the studio, or the lecture theatre in this case. And I'll try and make this less boring. We're going to have a few different kind of props in this one. So if we need to, we'll employ the one we need to at the right time. Alright, so what we're looking at here is how far do you think an EUC can push a car? So we're going to do some math, but I'll make it less boring, and we're going to look at a video. So we're going to have a video on here showing what I'm talking about. And we're not going to make the EUC look any better than it really is. We're going to look at real numbers. Like, for example, the battery. We're looking at a King Song 16X, which has a 1584 watt hour battery. It's got a top speed of 50 kilometers per hour. And it's got a motor rated for 2200 watts sustained. You're not going to ever get 1584 watt hours out of a King Song 16X. I mean, yes, you can, but you're going to have to be riding at like 18 kilometers per hour, like 11 miles an hour, for the whole ride without ever stopping. So you're going to be riding like all day long to try and squeeze that out of your King Song 16X. It's never going to happen. In real life, in most situations, you're going to get about half of that. especially when you're riding hard, you're going to get less than half. So what I did, I went ahead and did some calculations. So we don't bog down this video. I'm not going to do that in this video. But what I worked out is that at 12 meters per second, so it's around 40 kilometers per hour. So not quite the top speed of the 16X, close to top speed. You're only pulling 732.25 watts, right? But you're only going to get 1271.25 watt hours. See that? So, in real life, you don't have 1584 watt hours like the manufacturer says. You've only got, where's my other color here? You've only got, in this case, in our case, you're going to have 1271.25 watt hours. So that's your real watt hours. But you're only going to be drawing 732.24 watts. See that? So you're not going to be asking everything from the motor. You're only going to be drawing like a third of what the motor can do. But even so, can you see that? Even though you're only asking a third of what the motor can do, you're still not even getting the max watt hours. You're only getting 1271. So just see, like, I thought that's interesting to note. So you're going to get far less than what they say. And we're going to account for that. When we work out how far can a Kingsong 16X push a car, we're not going to say, oh, we're going to assume this to make it look better. We're going to use the lower number, the real number. So, with that in mind, let's proceed. How are we going to work this one out, guys? How are we going to do it? Well, let me just say, I want to light this one up now, actually. Make this video a bit less, like, mundane, you know? Because I bet you a lot of people, like in the last video where I had all the math, I reckon it would have been split where half of the people would have just quit the video because it's, you know, if they don't understand what's going on, they'll probably just go away. And half of you guys, I reckon, were interested and stuck through. So I'm hoping now I can explain it in a manner where more people will stay. And I'll just warn you though, it gets pretty tedious. Like, it gets into like professor plus levels of mathematics, you know? But don't worry, I'll speed through it like in a way where we're not going to bog down the video. We're just going to like get straight to the interesting bits. So let's do it. Well, first things first is you draw a diagram. Let's say this is the car. Got two wheels. And an EUC rider. We'll make the EUC green. Because it's a green machine, isn't it? Is pushing. So like you saw in my other video, we had a diagram of an EUC rider. Well, in this one, he's pushing a car, isn't he? See that? Makes sense. That's what we're looking at. So that's how you'll do it. If you're pushing a car, you're just pushing it from behind. So what we're going to assume is that the whole rider is ducked behind the car, meaning all the aerodynamic load, all the wind resistance, is going to be on the car. And the rider has no effect on the wind resistance of the overall system. Basic assumption. And we're on a flat road as well. So, yeah, we're not going up a hill, we're not going down a hill. Perfectly flat road. And remember, the question is, how far will this 16X be able to push the car before its battery goes flat? So from a full charge, assuming. And what do? You draw the forces. So you got a force here because of the EUC rider. Call that F. Call call it F1. And you've got your resistive forces. So you've got your aerodynamic load. You got FD, let's call it. And you've got the rolling resistance on the tires. And that's going to be fairly significant in this case because we've got a whole car. Call that FR. And I didn't draw the arrow longer for any reason because we don't know yet how big either of the forces are. Okay, so those are our two resistive forces, and we know that aerodynamic load, the equation for that is simply half of rho v squared CdA, where this rho is your air density. So I'll just write that here. Rho equals 1.3 kilograms per cubic meter. That's your air density. V is your velocity, so that's what we're going to try and find. CD is your coefficient of drag, which is, for this example, let's just use some ballpark figures. Let's use 0.37. That's kind of typical for your average car. And frontal surface area, let's use 1.85 meters squared. Again, typical for a medium-sized car. Alright, so what's your rolling resistance? Well, it's a simple equation. That's just your coefficient of rolling resistance times your downforce, which is mg. Alright, because you've got a downforce of mg acting on the vehicle. And the rolling resistance is just that. And for our coefficient of rolling resistance, we're going to use a typical value of 0.03, which is typical for an average road tire on asphalt. So, continuing on, and we know, and M is the mass of the vehicle, so we're going to use 1,400 kilos, which is about 3,000 pounds. So that's M. And G is gravity. We know that. It's just a constant, 9.81 meters per second squared. Alright, so we know all these numbers. Now we can proceed. Let's light this one up. Let's take a break. And stick with us, guys. Just stick with us. Even if you're not understanding this fully, just hang around because it gets interesting. I'm going to put all this together now. And we're going to actually answer this question, which was how far can this 16X push this car? And it's going to answer how fast can it push it too. Because we're going to need to know how fast it can push it in order to know how far it will go. So interesting, isn't it? Personally, I find it fascinating that using these kind of like beautiful looking equations, we can answer real world things like this. You know, it's kind of like magic, if you ask me. But yeah, let's continue. The next step is interesting. First, the next step. What is the next step? We got. Oh yeah, that's right. So, what we're going to do is use a simple formula that says that power equals force times velocity. Force times velocity. It's very simple. And how much power are we generating at the 16X level, at the EUC level? 732.24 watts. Alright, so the power being generated here equals 732.24 watts. We're pushing with a force of F1, that we called it, right? And what do we know? We know that in equilibrium, so when the car has reached a steady state, a steady speed, right? Because think about it, when you first start pushing a car that's not moving, it's going to speed up, right? and then it's going to reach a speed and it's going to maintain that speed based on how hard you're pushing it, right? So when it's at that top speed that you're going to reach, you've got equilibrium, meaning the force here is equal to the resistive forces. So F1, let's write that. F1 equals half of rho v squared CdA plus CRmg. Alright? That plus that. See? Simple so far? And now we employ that simple equation here to say that, so we just plug it in. So this becomes F1, see? So power equals F1 times velocity. F1 times velocity. Power equals F1 times velocity, which is equal to half of rho v cubed CdA plus CRmg v, which is the velocity. So all I did was multiplied both terms by v. That's a simple step, I guess. Now, what's next? Well, gotta think. Whoa. We've got a cubic, don't we? We've got a cubic equation. We can solve for velocity, which is important, which is going to tell us how fast we can push this car. Like I said before, the harder you push it, the faster you're going to reach. And this is going to tell us exactly how fast. Once we solve for v though. So this is where it gets a bit hairy. So you might want to skip. If you really don't want to get a headache, then maybe skip to this point here, alright? Skip to there. If you want to see some real mathematical trickery, wizardry, then hang around. We're going to solve this cubic and we're going to find how fast we can push this car, and then it's an easy step to go on and find how far we can push the car, which is what we were doing from the beginning. It's what the whole video is about. So what are we going to use? I'll try and see if I can remember this equation. If not, I'll just look it up, but I'll try and remember it. I'll do it up here. You ready? Doing this live. I'll draw a box here to like give myself some space. Alright, so for x cubed plus px plus q equals 0, x equals the cube root of negative p on 2 squared plus the square root of... Nah, I can't remember this. I'll just look it up. I've written it down somewhere. This is just like a known equation. Where is it? Oh, it's close. Q12. Oh, okay, so I was on the right track. That was a Q. Plus. And that's it there. Pretty ugly or beautiful, depending on how you look at it. But yeah, I was so glad I found this equation too, because I was like, when I was doing, like looking into this, I was like, dude, I'm going to need some kind of equation to solve this. And it looked like there was nothing out there. And this one video I found on YouTube, it was called like, why don't they teach this old equation or some shit like that? And it was exactly what I needed. So anyway, let's continue with this. We're going to use that equation to solve this. So what do we need to do? We need to divide. We need to get it in this form here. In that form. So we want, basically v becomes our x. Right? This is our variable. They're using x because that's like typical in algebra. But our variable is called v for velocity. So we want the v cubed to be on its own. Meaning we're going to want to divide all of this by half of rho CdA. See, because you've got the v cubed term here. So that means 2p on rho CdA equals v cubed plus cr dot 2cr mg rho CdA on rho CdA times v, all times v. And then one more step to get it into that final form. So I'd say therefore, actually let's leave some space down here for the net because we're going to have to, so I'll say therefore v cubed plus 2cr mg on rho CdA v take 2p on rho CdA equals 0, and we've got it in the form we want it. Now we can just use the expression that we have to solve for v. And we've got it, guys. We've got our final velocity. Awesome, huh? Not quite there, but in 1 minute we're going to beat this. Don't go away if you're still here. I'm excited. Let's fuck this thing up. Let's do it. Potentially the most important one of all is this one. Inspiration, guys. Alright, so let's just do it. Let's write it out. We've got v, because remember v is our x. Oh, actually, let's write what q is. So our q is essentially, so our p is this. So this here is p, and that there is our q, right? So that means p equals 2cr mg on rho CdA, and q equals minus 2p on rho CdA. Alright? And now we use all that. We'll use that to write our expression, which means it's going to be v. And this is it, guys. We're doing it. I'll do it in green, actually, because it's going to be our final expression. V equals the cubed root Actually, green isn't the best color because you can barely see it. We'll do it in red. V equals the cubed root of negative q on 2, so that would be that on 2. It would just be p on rho CdA. CdA minus the square root of q on 2 squared. So it'd just be that squared, which would just be that p on rho CDA all squared plus p on 3 all cubed. P 2CRMG on 3 rho CDA all cubed plus rho CDA all cubed, and that's it. That's the equation. It's a monster, but that is the equation that will give you the answer to how fast this car is going to go. How fast? That fast. And you might think, what the hell does that mean? Well, you got to plug in the numbers. It depends on so many variables, doesn't it? How heavy is the car? Well, we're going to say 1,400 kilos in our example. How dense is the air? Well, we're saying 1.3, but that's at sea level. Say if you're like higher up in the mountains, then that goes down slightly. Coefficient of drag, that depends on the car's design. The area, surface area, again depends on the design and how big the car is. And coefficient of rolling resistance depends on your tires, depends on the road. Your mass, again, depends on the car. Gravity, pretty much constant, but it also depends on elevation technically. It changes very slightly. But so you can understand what's going on here. And so in this equation, that's all we've got. Oh, and P is that there. That 732.24 watts. So I'll just write that here. P equals 732.24 watts. What else? That's everything. So if you look at all the terms in this big ugly equation, they're all found on this list here. Okay? So now we can just go ahead and work it out based on the numbers we've chosen. Alright, so the answer is 1.7712 meters per second. I don't know if you can see the screen on the calculator here, but we've got that equation, that bit in red, we've got it on here on the calculator. This is a pretty cool calculator. It like shows you the exact equation you're putting in. Maybe you can't see that, but anyway. The answer is 1.7712 meters per second. I'll write it up here. V equals 1.7712 meters per second. In kilometers per hour, you just multiply it by 3.6. 6.376. 6.376 kilometers per hour. And in miles per hour, 3.96 miles per hour. Alright? But what we wanted to find out was how far could we push this car before the battery runs out. So we're pretty much there. The next step to find that answer is very simple. All we've got to figure out is how long can we push it for. Because we've figured out how fast we're going to be pushing it. But how long are we going to go for? Right? Well, we know we've got 1271 watt hours and we're using 732 watts. So you just divide that number by this number and that gives you how many hours. So let's work it out. 1271.25 divided by 732.24 equals 1.36 hours. So time, we'll call it T, equals 1 point, what is it? 736 hours. But we need it in seconds, so you just times that by 3,600. 6250 seconds. So it's that many seconds. We're moving at that many meters per second, right? So our velocity equals 1.7712 meters per second. And we're going to do it for that many seconds. So how far are we going to go? You just multiply that by that. So 11,070. So distance equals time multiplied by velocity. Right? Time, oh, I should write it the other way around. That's how you normally see it in like a science book. V multiplied by time, which is equal to that many meters. Alright, so all I did was multiply this by this. I get that many meters, which is 11.07 kilometers, which is equal to 6.88 miles. So there's your answer. That's the final answer. And that's what we came to see. And to me, it's pretty amazing how something like the 16X, or like, you know, something so small, can push a whole car this heavy for that long. 11 kilometers. That's crazy. That's like most people's commute to work. Do you know what I mean? It's kind of mind-boggling. Granted, at a very slow speed of about 4 miles an hour.